We've learned our 3 rules. We've reminded ourselves about the kind of quantum number rules. So let's start applying this and start doing electron configurations. The first kind of configuration we're going to learn is called orbital notation. Some people call it box notation because we use boxes here. And sometimes online you'll just see it with lines like this. Oopsies. You'll just see lines drawn like this. But if you do that, you need to go out of your way to group, show how those are grouped together, like these 3 2p orbitals belong together. So I prefer to use boxes with students because you can definitely tell that these 3 orbitals are grouped together. So I'm going to stick to box notation. And you can see, I've already pointed this out to you, but when there are multiple orbitals in a sublevel, when you've got p or d or f sublevels, you join your orbitals together because all 3 of these orbitals have the same energy. So we join them together. You must label these boxes. You must label them with the energy level and the sublevel. All right, oxygen. Oxygen on the periodic table has the atomic number of 8. And for the purposes of this assignment, we're just assuming that all of the atoms that we're dealing with are neutral. So if we've got 8 protons, we must also have 8 electrons. So I need to draw 8 electrons in this orbital notation. So let's start placing them. 1s, then 2s, then 2p. Okay. First, I fill the 1s sublevel. It takes 2 electrons to fill that 1s sublevel. Now that sublevel is full. So the 3rd electron I place has to go in the next lowest available energy level. That's the 2s. 2s comes next. Again, we fill up the 2s sublevel. So now I've placed 4 electrons. I've got 4 more to go. How do I place those 4 electrons? This is the p sublevel, and remember we have to follow the empty bus seat rule. So I put in 1, 2, 3, each on their own separate bus seat, and now I start doubling up. Now I've drawn 1, 2, 3, 4, 5, 6, 7, 8. I've drawn all 8 electrons, so this is a complete orbital notation configuration for oxygen. A similar way to do an electron configuration, sometimes this is called, a lot of times this is just called electron configuration, sometimes it's called longhand electron configuration. This is the most common type of electron configuration. It shows all energy levels and sublevels, but not the orbitals. So each term has 3 parts. The big number in front, like this 2 that I've circled here, tells us the energy level, our main energy level. The letter tells you what sublevel you're in. And then the superscript, like the 4 circled in green here, tells you the number of electrons in that sublevel. So here I've written this complete and correct example for electron configuration for oxygen. I am representing the same electron configuration that we completed on the previous slide. Notice that my 1s sublevel had 2 electrons in it, the same way I had 2 arrows on the previous slide. Similarly for the 2s sublevel, I had 2 electrons, 2 arrows drawn in that box on the previous slide. And I had 4 electrons drawn in the 2p sublevel on the previous slide. So I'm representing the same information in a different way. This actually has slightly less information because it doesn't show you, I don't have to worry about the empty bus seat rule when I'm doing a standard longhand electron configuration, because we just say, oh, there are 4 electrons here, and I don't show you the spins of those electrons. So this notation is slightly simpler than the orbital notation I showed you previously. Again, just showing these side by side. Orbital notation, electron configuration convey the same information, but orbital notation gives you more detail about those electrons and their spin. So let's practice. If we want to write the orbital notation and electron configuration for the following elements, it's better to start with the orbital notation, I think, when you're first learning these. So for titanium, if we look up titanium on the periodic table, we see that titanium has 22 protons, and therefore for the purposes of this example, we're going to also place 22 electrons. So I've already written for you some orbitals in the correct order: 1s, 2s, 2p, 3s, 3p, 4s, 3d. Start filling them in with electrons. Again, following the Aufbau principle, where we completely fill the low energy levels before we go higher up. So I placed 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I just have 2 more to place. I have to follow the empty bus seat rule, so I'm going to put those electrons in separate orbitals. It helped me to use my periodic table method to know how many boxes to draw. So this is one of the reasons I like to use my method, because I know that titanium is in the D block. So I know that it's in the 4th period. So I know that titanium is going to end in the 3D sublevel. So that kind of helps me predict how many boxes I need to draw. Let's look at another example. Potassium. Potassium is in the 4th period, and it's in the S block, so that's how I know to write out all the electron configuration up to the 4s sublevel. Potassium has an atomic number of 19, so I need to place 19 electrons. So let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Zinc. Zinc, like titanium, is going to end in the 3D block. Zinc has 30 electrons, so I have to draw 30 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now, I also said that we should write the orbital notation for these same electron configurations, just so that we get in the practice of doing that. So let's do that. We have 2 electrons in the 1s sublevel, so we call that 1s2. 2 electrons in the 2s sublevel, 2s2. 6 electrons in the 2p sublevel, we call that 2p6. 2 electrons in the 3s sublevel, 6 electrons in the 3p sublevel, 2 electrons in the 4s sublevel, and then just 2 electrons in the 3d sublevel. Let's do the same thing for potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And now for zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Notice that the maximum number of electrons that P can ever have is 6. The maximum number of electrons that S can ever have is 2. The maximum number of electrons D can ever have is 10. And although it's not shown here, the maximum number of electrons that F can ever have is 14. Now, a sublevel does not have to be full. Notice this D sublevel does not have 10 electrons, it only has 2, because this electron configuration ends at that sublevel, and it's not totally full. Similarly here, this 4s does not have 2 electrons in it, it only has 1, because that is where this electron configuration ends. And I do want to look a little further ahead on your periodic table, do a little bit more complicated one. So let's do Mercury, since it's the biggest one on here. We have to place 80 electrons. Again, it's helpful to know where I'm going to end. Mercury is in the D block, and it's in period 6. And remember, that's not 6D that I'm aiming for, it's 5D. Remember, you subtract 1 from the energy, 1 from the period number to get the correct energy level. So I'm going to end with the 5D sublevel. So I need to kind of know what my target is so that I don't just go crazy and write down more than I need to. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d, and remember this is where I said I would end. Mercury is in the 10th position in the D block. So Mercury will have a totally full D sublevel. Just to check, I'm going to check to add up all of my superscripts here, because all of those superscripts should add up to 80 electrons if I've done this correctly. So 2 plus 2 plus 6 is 10, plus another 10 here is 20, plus another 10 is 30, plus here is 38, 48, 54, 56, 70, 80. So my electrons do add up to 80 as a kind of extra check, and I have the correct electron configuration for Mercury. I always want you to give me your electron configurations in this order. The order that you get from using the diagonal rule, or the order that you get from looking at the periodic table. It's the same order. I want you to give me this order for filling your electron sublevels. Not all resources on the internet will give you electron configurations in this order. There are reasons to use different orders, but those reasons will not occur in this class. I want you to always give me your electron configuration in this order. Therefore, it is important that you come up with your electron configurations yourself and do not just do a Google search to figure out your electron configurations. First of all, that won't help you prepare for the test. If you just Google search things instead of using your brain and practice using your brain. But secondly, there are exceptions to this filling rule that you do not need to know about at the Chem 1 level. Not everything follows these exact rules. There are various exceptions to the filling rules, but they are beyond the scope of Chem 1. If you give me one of those alternative electron configurations, I will know that you used Google instead of your brain. And if you can't give me the justification for why there's an exception to the filling rule, then you should not be giving me the exceptional electron configuration. Please use your own brain, your own mind, not Google, to come up with your electron configuration. I hope this helps.